The topic of this video is activation energy and the Arrhenius equation. So at the end of class on Friday, we had been talking about this idea that in order for a reaction to occur, the reactant molecules have to collide with each other. And more specifically, they have to collide with each other in the correct orientation. So we had been looking at this reaction of carbon monoxide and molecular oxygen reacting to form carbon dioxide. And we had said that since the structure of carbon dioxide, which is what we're trying to form, looks something like this, that the second option, where the carbon from carbon monoxide is colliding with the oxygen, would be more likely to produce this reaction because this was the orientation where the two atoms that were involved in this carbon-oxygen bond that needed to form were colliding with each other, all right? So when the atoms that are involved in a bond that needs to form collide with each other, the reaction is more likely to occur, the bond is more likely to form. However, we had also said that collisions in the proper orientation alone are not enough to produce a reaction, all right? We had said that molecules also need to collide with enough energy for the reaction to occur, specifically enough kinetic energy. So what this actually means is that these collisions have to happen, they have to be strong enough to form new bonds and trigger old ones to break. All right? So these have to collide with a certain amount of energy in order to cause both of these things to happen. So what does this actually look like? Let's walk through it with this reaction example here. So we have some reactants that we're starting with. I'm going to call those R for ease. And we have some products that we end up with. But what is happening in between? How do we go from R to P? What is happening in between those two stages? So what's happening is that those reactant molecules are coming together, they're colliding, and when they do that in the right orientation and with enough energy, they're able to form this activated complex. And this is why we need a lot of energy when we're colliding, because the activated complex is a very high energy state. All right? And it's important that it's high energy because that allows it to then decay into the products, which would have a lower energy than the activated complex. You may also see this called transition state. So this state decays into the products. And it does this very quickly. This state is not around very long, all right? It's very short-lived. In fact, it's really hard to even see this. And you have to use very, very sophisticated instrumentation to even see that this is happening, all right? So our reactant molecules are colliding, they're coming together, they're forming this very high energy activated complex or transition state. That transition state, because it's so high energy, it's very unstable, then decays into the products and you have your reaction. All right, so that's how we go from our reactants to our products. So let's look at what this looks like energetically. So this is called an energy diagram. And so on the y-axis, we're plotting energy. And on the x-axis, this is like how long has the reaction been going on. So we're going to call that reaction extent. And so we start with our reactants. So this is our N2O and our nitric oxide. And then they're going to collide with each other with a lot of energy. And that's going to allow them to form the activated complex. Which then decays into the products. So that's our NO2 and our molecular nitrogen. all right? So this is our energy diagram. Reactants start with some energy. They collide with each other to form this very high energy activated complex state, which then decays into the products. So this energy difference here, let's draw some dashed lines so it's a little clearer what we're looking at. So the energy difference between the reactants and the transition state is called your activation energy. So your EA is your activation energy. And you can think about this as the energy needed to reach the activated complex. So activation energy, difference between your reactants and your activated complex. The energy difference between your reactants and your products is actually just your change in enthalpy. So your change in heat, because this is at constant pressure. All right. So here I'm showing you an exothermic process because we have a negative enthalpy change, which means that heat is being released. So our products are lower energy than our reactants. But that's not always the case. Sometimes we can have an endothermic process. And in those cases, the energy diagram would look like this. We still have our reactants, and they're still moving towards this high energy transition state or activated complex. There's still some activation energy associated with that, but now we have a positive enthalpy change because the products are higher energy than the reactants. Okay, so this is what it looks like if you have an endothermic reaction. Your reactants start with some energy, form the activated complex, which is very high energy. The activated complex decays into the products, which are still higher energy than the reactants. So this would be endothermic because some heat had to be put in to the system in order to have products that have higher energy than the reactants. All right? But how does any of this relate to what we've been talking about with all the kinetics and the reaction rates? So it turns out that our activation energy, our EA, is actually quite related to our rate constant, that K that we've been working with. And it's related through this equation called the Arrhenius equation, right? So this is saying that our rate constant is equal to this A, which is a frequency factor that is related to how likely collisions with the correct orientation are. All right. So high values of A, this is called a frequency factor. It means that we're colliding with we have collisions in the correct orientation with high frequency. All right, so high A, high frequency of collisions with the correct orientation. That ends up giving us a faster reaction rate. All right, so that's that A. How likely are we to collide with the correct orientation? How frequently is that going to happen? If it happens a lot, we have a high A value and we have a faster reaction rate. All right. R is our gas constant that we've been using, that we used a lot when we were talking about the gas laws. So most of the time for us, that's going to be 8.314 joules per mole Kelvin. T is our temperature. Notice that this has to be in Kelvin. So temperature must be in Kelvin. And that should be apparent when you look at these units and if they cancel out, all right? And then we talked about the frequency factor. So these are all of the components that affect a reaction rate. So let's talk a little bit more about temperature specifically. So we had said that our reaction, or our Arrhenius equation, is this equation. And we see that temperature is involved, all right? So what we talked a bit about A, didn't talk a lot about this. This term is the activation energy component. And RT tells you how much energy the molecules have when they collide. So for a reaction to actually occur, this needs to be higher than the activation energy. So this kind of explains why temperature can really have an impact on our reaction rate, because at higher temperature, let me change my color. So at higher temperature, the molecules have more kinetic energy. So more molecules are going to be able to collide with enough energy to get over that activation barrier, or the activation energy. So more molecules are likely to have sufficient energy to overcome the activation energy. Which you might also hear called the activation barrier. That means the same thing as the activation energy. We call it that because you need to be able to overcome that activation energy in order to react. So it's kind of being able to get there is the barrier to the reaction. All right. So at high temperature, much more likely. So this is actually incredibly useful because we can measure rates. We've talked a lot about that. We can measure temperature with a thermometer. So if we collect rate experiments at multiple temperatures, we can actually find the values of our activation energy and our frequency factor. And that is going to be the subject of the next video.